In today's video, I'll be providing a brief summary of my airport traffic management simulation project. And hopefully by the end of the video, you understand the main concurrency concept I've used within this project and why I've decided to use them that way. So, without further ado, let's get into it. We begin by first discussing my motivation for this project. So I created this simulation as a way for me to get my feet wet in concurrency programming in C++. Now, why did I pick airport management? Well, it was an aspect of travel I don't see many people talk about, and I think it's an interesting problem to solve. This project will handle a very small part of airport management, that being ensuring that airplane traffic is managed in a way that prevents collisions. So, how did I go about solving this problem? The first was that I broke down the airport into a series of interconnected runways and taxiways. Each runway will handle its own traffic and thus share the burden of traffic management and decentralizing the traffic control. Each runway can only have one airplane on it at any given time, and arriving airplanes must queue up and wait to cross until the runway is completely clear. While this approach is simple and I say easy to implement, it sacrifices efficiency as it does not consider the size of the runway. Take, for example, if we have a runway the size of Australia's breadth. If airplane 6 in this example is all the way across Australia, airplane 2 and airplane 1 still cannot enter the runway because airplane 6 is still in the runway. While this is a massive exaggeration, airports in real life are still pretty large, at least large enough to have at least 2 airplanes moving on the runway simultaneously. Now, my solution also includes a port. Ports were added primarily because I wanted to introduce randomness into the simulation, but they also serve another purpose, which is to replicate real-life airports even more. Now, my solution consists of 4 main topics, or 4 main points. This is thread management, the airplanes themselves, the runways, and the ports. We begin by first discussing how I manage threads in this simulation. Each class, which is airplane, runway, and ports, are all run on separate threads. More specifically, their main function are run in separate threads. The main function of the whole program is only responsible for initializing and starting up the simulation and nothing more. Creating threads, however, requires us to manage their existence properly, which brings me to my next point. Each class will inherit from one main parent class, which will handle this thread management. This main class will have the ability to store all created threads within an object into a vector, and B, call the join function when the object is destroyed, thereby preventing any zombie threads from staying alive. Now, with all these threads floating about the simulation, we must be careful in managing the shared resources between them. And a crucial one of these resources is standard output. I can always forego the use of standard output, but debugging without it is extremely difficult or very difficult, so it's necessary that I have standard output in this program and used by these threads. However, if we do not have a proper way to manage these threads and their access to the shared resource standard output, then we can get some pretty interesting results from the race conditions that will occur. And in this example, we have multiple threads in blue rectangles writing to standard output and outputting a very intelligible output. Now, how do we fix this? We fix this by using a programming object called the mutex. Now, the mutex will prevent simultaneous access of a shared resources by giving only one thread the access to the shared resource. This is done by having one thread acquiring and locking the mutex. This prevents other threads from acquiring it, and because it is the only method of accessing standard output, this will also block the thread. It is only when the mutex is released the next thread can acquire and locks the mutex and subsequently use standard output. Airplanes were designed to only have one role: move across the airport. And because of their very simplistic role, I've created very simplistic state machine with a wait state and a runway state. Later on, however, I decided to incorporate a port, and after countless hours of debugging, I found that defining a new state for the airplane was needed to accommodate it. So the final state machine looks like this, where we have the wait port where the airplane is stationary, doesn't do anything. We have the runway state where the airplane is moving across the runways, either to a port or to the exit of the runway. And we have the port state where the airplane is just waiting for a timeout at a port. Now we get into the meat of the program, which are the runways. The runways again have only one goal: permit only one plane on its tarmac at any given time. To achieve this behavior, there were three problems I needed to solve. First, how do I block the planes from entering the runway? Second, how do I know when the runway is clear? And third, how do I let the planes in the runway? We begin by first answering the first question: how can I block the airplanes? To block the airplanes, we can push them into a queue, and we can create a future object where we can call the wait function as to block the thread. Now that the airplane is waiting, we need a way to signal to the runway that it is clear. This is easily done by having a variable that represents the state of the runway. Now the runway main function can continuously poll this variable to check whether the runway is clear or not. So when the runway is clear, how do we let the airplanes back into it? In order to do that, we can pop it off the queue, and then we can call promise.setValue. This will unblock the thread and allow the airplane to move again from its stationary position. As we can see in this thread diagrams, the lines are the threads. The move function is the airplane main function. The process airplane queue is the runway main function. As we can see from the move function, we call future.wait, which blocks the function. It only resumes the move function once promise.setValue is executed. Promise.setValue is executed only when the runway is clear, which is a signal we get from the process airplane queue. Now, ports are a section of the airport where the airplanes dock into terminals. In my implementation, a port can have multiple terminals, each accommodating only one airplane. If an airplane enters a port, the port will be clear if the plane enters a terminal or exits the port. Combining the first constraint, where there can only be one plane for each terminal, and the second constraint, where there can only be one plane in the runway, I created an interesting problem. What would happen if all the terminals were occupied? Well, you would get a deadlock. As from this example, airplane 6 is in the runway, but airplane 6 wants to go in a terminal which is obviously not available. Whereas on the other hand, airplane 2 wants to go into the runway, but it can't since airplane 6 is on the runway. And because of this, we have just created a deadlock. So how do we solve this deadlock? Well, we can solve the deadlock by guaranteeing that one of the shared resources is freed before it can be obtained. In this case, I chose the runway to be that freed resource. We only let airplanes into the runway if there is an available terminal waiting in the port. If there isn't, they are going to be stuck queuing out of the runway, at the entry of the runway. This allows for any airplanes in the terminal to go into the runway and thereby freeing the terminal resource and hence solving the deadlock. Now we're at the end, where I must admit that this is a very simplistic view of airport management, and a lot can be done to improve it so it can accurately replicate real-life airports. Some of the current limitations of the program are as follows. You've got long wait times, there's very inflexible plane movements, some shared resources are not properly protected, the airplane state machine is dependent on the structure of the airport, and the GUI would need some significant improvement to, replicate the airport structure. We can reduce long wait times by either reducing the amount of queuing or introducing new rules for the length of each runway. We can have airplanes follow a given route automatically regardless of the shape of it. We can have shared resources either be protected by mutexes or designed in a way where it isn't shared. We can make planes be adaptive to any airport configuration, and for the GUI we can either try a web-based GUI or a local GUI. Hopefully you've understood how the simulation all works, at least in the bigger picture. Remember to like and subscribe.